This is Professor Derf Seitz. This Java tutorial focuses on arithmetic operators. This program has a number of comments at the top. The arithmetic operators are binary operators. That means they have two operands, one on the left and one on the right side of the operator. Here are the operator symbols: plus for addition, minus for subtraction, a star for multiplication, / for division, and there's a modulus operator that gives the remainder after division. The operator precedence is parallel to that in mathematics. Parentheses define the highest precedence. Next are multiplications and divisions from left to right, including this new modulus operator. Then additions and subtractions from left to right, and finally the assignments go from right to left, and they're the lowest precedence. There's some precautions about divisions. We'll see those when we get down into the program. And here are some notes on typecasting, which is a promotion or conversion of a lower precision or smaller width operand to a compatible higher precision operand. For example, an int can be typecast or promoted to a double because a double has a wider range of values than the int does, and the int will fit in the double. But you can't go the other way. Some doubles will not fit within an int. There's two kinds of typecasting: implicit, automatically done by the Java, and explicit, the programmer has to specifically indicate that the cast is to be done. Here's the syntax for the explicit typecast. You take the variable name or the calculation expression, and out in front of it, inside parentheses, you have the data type that you want to cast it to. Note that typecasting produces a temporary value. The original variable is not changed. In the program here, we have one method, the main method. Class is called Java Arithmetic Operators. We set up some ints to be used in the calculations. Operand 0 is a 0, 1 is a 1, operand 2 is a 2. We have two different results: an integer result, I result, and a double result, D result. First addition, we have this statement here: I result equals 1 plus 2. We're adding two literals, both integers, 1 plus 2, and then we're going to display the result with this system out print line to the system console. And there's a note here about the plus sign over here, right there, that plus sign. That's string concatenation. We have a string literal here, which is a label for our output, and then we have our int here, but this plus sign is string concatenation. So because print line needs a string parameter, and we're need to concatenate a string with a string, iResult will automatically be converted to a string representation, and then that will be combined or concatenated with this label to give us the full string for output. The next addition, instead of literals, we have variables. That's where the power of arithmetic operations comes in computing, because you can define variables and they can take on different values from different sources. Subtraction, we have the minus operator here. Multiplication, the star operator. Division, the /. This division here is producing a double result, and this 2.0 and this 3.0 are both double literals because of the decimal point. Next, we look at division with integer operands. When you divide two integers, then that division truncates any remainder without rounding. This is called integer division. Here are some examples. If we take 2, which is an integer, and divide it by 3, which is also an integer, then it's going to truncate any remainder and only give the whole part and assign it to the double. To prevent that, you cannot be dealing with two integers in the division. So one way to prevent it is make one of them a double literal. Like this 2.0 is a double. When you do arithmetic with a double and an integer, it will convert the 3 to a double as well, and double arithmetic will take place here without this truncation of a remainder. Another way to convert the 2 to a double is to explicitly cast it, as we see here on the 2. That will happen first, and then the 3 will be converted. By the way, on all these operations with literals, or even with operands, like this one here, 7 times 9, when 7 is multiplied by 9, you're going to get a temporary result, and that temporary is going to be assigned to the left-hand side in this assignment statement. Back down to division by 0. This next block of code here shows division by 0. Division by 0, as we see here with operand 0 being a 0 value, creates a runtime exception. We can try that right now. If we compile this, it does compile, and then when we run it and bring the output into view, we'll see here the divide by 0, we get an exception. It says slash or divide by 0, that's an exception, and the program stops, it crashes at that point, it will not execute anymore after that point. Let's close that output. So you cannot divide by 0. We'll see later in a later tutorial about how to catch these exceptions and handle them in the code, but for now we're just going to comment out this whole block of code, save the file, recompile, and then going on to the next thing. The modulus operator is the remainder after division. Here we have 15 modulus 3. The remainder, 15 divided by 3, is 0, so there's 0, that's it. 17 divided by 3, 3 goes into 17 5 times with 2 left over. So the modulus operator will be a 2 there. Here we see order of operations. 3 plus 5 times 10, the multiplication has higher precedence than addition, so the 5 times 10 will happen first, giving 50, and then adding 3 to that to give 53. To make it clearer, you can put parentheses in the code so that the people reading your code, trying to understand it, don't have to constantly think about the order of operations. Here it's very clear that the 5 times 10, because of the parentheses, will happen first. If you want to change the order of operations, you can use parentheses. Here we're doing 3 plus 5 in parentheses to give 8 first, and then multiplied by 10 will be 80. Finally, overflow. This example here, we take 2 billion plus 2 billion, and these are integer literals because they do not have any literal characters at the end of them, like a L for a long or anything like that. These are both integers. They fit within the size of an integer, but when you add them together with integer arithmetic, the temporary will be an integer, but it will be too big for an integer, and you'll lose some of the data and get a strange result. If you go down here and try to assign it to a double, the double result, it doesn't make any difference. The temporary will still overflow. This third example in this group, each one of the operands, because of the decimal point, is a double. So the temporary will be a double, there will be no overflow, and it will assign it correctly to the result. Let's run this program and bring the output into view. I need to make this a little longer. Alright, addition. 1 plus 2 is 3. Operand 1 plus operand 2 is 3. Subtraction, the 1 through operands, that's a 1 minus a 2, is a negative 1. Multiplication, 7 times 9 is 63. Division, this is a division of doubles, not integer division. 2 divided by 3 as doubles is 2/3, that's 0.6666. And of course it only has so many digits of precision it can show. Integer division, 2 divided by 3 as an integer throws away the fractional part and you get 0 as an answer. To fix it with a 2.0, to make that a double, you get the right answer, or casting to the double gives the right answer. Modulus, 15 mod 3 is 0. 17 mod 3 is 2. Order of operations, 53, the 53, and the 80. And the overflow, the first two, you get the strange result as a negative number because of the overflow. The last one is correct. It's shown, the formatting here is the scientific notation. That's 4 times 10 to the 9th power, 4 billion. We'll close the output window, but we'll just leave the output window open. This concludes this tutorial.